So in this talk, I will discuss about the recent advances in iron making technology. I will touch upon first the blast furnace technology and its development, and followed by some recent technology in the area of alternative routes of iron making like direct reduction, smelting reduction, technologies like that. Okay, before I proceed, first slide, I am showing something is like a phase diagram. Okay, in x-axis is the temperature and y-axis you know the composition, oxygen and carbon. Basically, any product of iron and steel making are shown in this diagram. You can see this is the DRI, this is the hot metal, this is the steel, and this diagram is very nice diagram, and it is taken from Amit Chatterjee's book of hot metal production by smelting reduction, 2010. It gives a very conceptual view of the different products of iron making and the different processes. So you can see the product, first product is the direct reduced iron. And obviously direct reduced iron are basically almost a pure metal with certain amount of the carbon. And in case of the coal-based DRI, you can have around 0.1 to 0.2 carbon. In case of gas-based DRI, it can be even up to the 2% of carbon. So that's why this is the location. And you can see most of the DRI are produced around 900 degrees centigrade. Maybe in the coal-based DRI produce little higher temperature, maybe 1000 degrees centigrade. So its position is here, temperature at 900. And its composition, you can see the carbon is around maximum around 1 to 2%. Okay, so this is the location of the DRI in this diagram. And then you have the hot metal. Hot metal is here. And hot metal temperature is usually 1350 to 1400 degrees centigrade maximum temperature. And then its composition, obviously, hot metal is always saturated with the carbon because it is produced in the blast furnace, which is where plenty of carbon is there. So liquid iron gets saturated, and its composition around 4 to 5%, around 5% of carbon, you can say. Okay, so it is the position. There is 1400 degrees centigrade with 5% carbon. And this is the steel, crude steel as you can find, and then steel is produced in called a basic oxygen furnace, where basically you find the hot metal. What you do in the hot metal, you can see 4% carbon, 5% carbon is there. So you have to remove the carbon along with other impurities are also there like silicon, manganese, phosphorus. All you remove, and then your final composition will come here. In this diagram, that you can show the carbon composition is shown. It is around maximum around less than 1%, and you can find some amount of oxygen is there. Obviously, some residual oxygen will be there. That is also almost to the saturation level because we are producing by charging oxygen. Okay, so this is the product, steel product you can find. Now, this is the major three products, and how you can get to this product. That's why the different processes are available. And this DRI or the sponge iron that you get at comparatively lower temperature, and it is called the product of solid state reduction. Okay, so in solid state, if you reduce it, you can get this DRI. So you can find if your source is Fe2O3 and it is with 30% oxygen is there, as you know, stoichiometrically 30% oxygen, 70% iron is there. So 30% oxygen, and this whole oxygen is removed. Okay, at this 900 degrees centigrade at the solid state, and you can get the product called the DRI. And this DRI can be produced in presence of carbon, or you can use it, the reformed gas, to reduce it, and depending on that, the carbon composition is quite less. In presence of carbon, when you do, because since you are producing in the solid state, carbon cannot diffuse into it. The diffusion is a limitation. That's why your carbon percentage is very low. In case of the gas-based DRI, you can increase the carbon percentage by cracking the natural gas during the cooling of the DRI. I'll talk about that. That is the thing. So you can control by the natural gas cracking, and you can increase the carbon percentage. Higher carbon percentage is helpful for, obviously, for opening carbon. If it is higher, so liquid has become less, and you can easily make it. Okay, fine. So this is the product, and then when you get this DRI or hot briquetted iron, whatever it may be, so this will go and you can melt it in electric arc furnace, and you can directly produce the liquid iron because DRI contains very less amount of the carbon. In case of the gas-based, it may be little higher. Then also you do some amount of refining in the electric arc furnace, and you can directly get this, what is that called, the crude steel, liquid steel. That is our final aim, to produce the crude steel. Okay. So the scrap also will be there. Scrap is also another, you can say, the metallics that is available in the steel plant. And because of, but with the invent of the very advanced steel making technology like continuous casting, the scrap is depleting, and which is being replaced by the DRI certificate. Okay. So then electric arc furnace you can make, you can get the liquid steel. Now one that is the most conventional method of producing the liquid hot metal is by the blast furnace route. And in this route, what you do, if you see that most of the oxygen is removed at around, in the solid state, you can see around 1000 degree or 1100 degree centigrade. In the blast furnace also, you remove most of the oxygen in the solid state in the upper part of the blast furnace. And then in the lower part is basically melted, and then the metal get carbonized in the liquid state, because in the solid state carbon diffusion is less, but when you make the liquid product, then carbon can easily penetrate into it, and then you come to a very saturation level, and then you can get a hot metal, basically liquid iron with around 5% carbon, along with some other impurities. Okay. So this is the blast furnace, and then you can take this hot metal, because it is a lot of impurities are there. Unless you remove this impurity, you cannot make it malleable. So you produce steel by oxygen charging in the oxygen, basic oxygen furnace. So you can call it is the BF route, BF and the basic oxygen furnace. So you can hot metal and then you can get the liquid steel. This is the very conventional route of iron making and very dominant even today. So dominant route of steel making is the BF route. Okay. And then you can find some other routes are coming, the red line, that is called the smelting reduction. And you can see that the most of the oxygen is removed at quite high temperature, very high temperature, and in the liquid state, around 1400 degrees centigrade like that. So in the liquid state, most of the oxygen you remove. Partially some amount of oxygen you remove in the solid state. In this case, in the smelting reduction process, the idea here is to get rid of complexities into of the blast furnace. In the blast furnace, what is there? You have a blast furnace otherwise a very, very complex reactor, but very efficient reactor. Heat transfer and you can utilize that is the heat transfer and mass transfer point of view. Blast furnace is an excellent reactor.
हाँ ये क्या भैया ऑनलाइन प्रोग्राम जो था FDP वाला ज्वाइन नहीं किया तुमने?
What?
हाँ हेलो?
हाँ. Is it the question to me? Okay, so this is the smelting reduction route. As I was telling, there's the blast furnace. In this blast furnace, you have both the reactor. That is, you have a solid state reduction taking place in the upper part of the furnace, and the lower part you liquefy it, you melt it, and then carbonize it. All the things take place in a single reactor. So you have a dry zone, you have a wet zone, and that is nicely interfaced by what is called a cohesive zone. But if you want to maintain this very intricate and complex structure in the single reactor, the major problem is that you cannot compromise with the raw material. The blast furnace, the raw material quality is very stringent, that's why, because you are running a very complex process. Okay, so the raw material requirement will be very high. So that's why the smelting reduction technique comes. This technique, I want to use inferior grades of raw material, right? So if I want to inferior grade of raw materials, then I have to change the reactor. I cannot continue with the blast furnace, because blast furnace can never allow inferior grades of raw material, because the permeability issues and a lot of other problems will come. Because in a single reactor, we are doing this. In smelting reduction, what happens? You split the blast furnace in a two separate reactor. Maybe in a solid, that is the solid state reduction, you can carry out in a one reactor that is called the reduction unit. Another unit is there that is called the melted gasifier, where basically all the melting and that is the rest of the reduction will also take place. Okay. So in smelting reduction, you have to, in most of the cases, it is this two-stage reactor. You have a reduction reactor where solid-state reduction takes place, where you can partially reduce the raw material, and then you can charge those raw material into the melter gasifier, where you melt it, and you take out the rest of the oxygen, and then you produce the a product, what is the hot metal, which is very comparable to the blast furnace. But here, what you can do, since you have a two separate reactor, you are not bothered about the quality of the raw material. You can use, that is the non-cooking coal, directly use the non-cooking coal and oxygen in the smelter gasifier, okay? And you can produce a similar quality of hot metal. So thing is that in the smelting reduction, the idea is to use an inferior grades of raw metal like non-cooking coal and even iron bearing solid waste from the steel plant, all inferior grades of raw material you can use, because you are changing the reactor. You have separated the two reactors into two parts. Okay, that allows you to use this inferior grades of raw material. And another thing is that in this case, since you don't require the coke and sinter like this, so you can cut off the ancillary units like coke oven and then sintering machine, all these things that basically pollutes the atmosphere. So that was the idea of the smelting reduction. So in the smelting reduction, there is the majority of the reduction take place in the liquid state, and then you get a product. Interestingly, the hot metal quality is comparable to the blast furnace, and sometimes it is much better than that of the blast furnace. Okay. So, and also at the same time, you can use simply non-coking coal to produce it. That's why this technique is so evolving. Only one problem is there in the smelting reduction process, that is the coal rate is little higher, little miles much higher. As a result, the export gas is very rich in CO. So unless you use that export gas for generating the power, this process will never be economical. So that thing is there. So off-gas utilization is very important. That is, off-gas credit is very high. So otherwise, so this is another route. You can find that you are reducing the iron ore almost in a very high temperature, okay, and then using non-coking coal, and you can produce hot metal, and then you can use either electric arc furnace or you can use BOF to produce the steel. And in some cases, since the hot metal quality from smelting reduction is quite good, you can directly use the electric arc furnace, and along with the DRI, and you can make some less amount of refining. Refining load is not that high in some cases of hot metal from the SR unit. So impurity load is not high. So you can mix up with this DRI and you can produce the steel in electric arc furnace. So that's why the electric arc furnace today is evolving, because the advantage of the electric arc furnace is that you can take in any proportion, the charge in any proportion. There's a cold charge and hot charge in any proportion you can use. But basic oxygen furnace or the LD furnace has a limitation on the cold charge, because it is an autogenous process. Heat is generated by chemical reaction. So it has a limitation of taking the cold charge. Some excess heat is generated from impurity oxidation. Impurity oxidation sustains the BOF process, as well as some excess heat is generated, and that you can use to melt some amount of the cold charge, but there is a limitation, around 20% you can use. So, but depending on your plant inventory, if you have nowadays, most of the plant has the DRI unit, and then, so you have a lot of supply of the solid metals. So if sometimes it happens that you have to charge 40% of the solid charge, electric arc furnace, you can use it. 40% solid along with, say, hot metal from the SR unit. So you can mix up, or the blast furnace and the DRI, you can mix up in 40-60, any proportion you can mix up. So you can use an electric arc furnace, that's why is now evolving. Okay, so next diagram I will show that thing. You can see this is how the electric arc furnace is coming up, and then if you compare in 1960s, then open hearth was there, and then BOF started coming in 2000. BOF was very dominating, and nowadays you can see the electric arc furnace almost the steel produced around 50% steel is produced by the electric arc furnace. So DRI electric arc furnace, DRI hot metal electric arc furnace. So this combination is coming up. So we have seen that is the two major routes are there. BOF route, that is one of the major dominating route, and that is that the DRI hot metal EAF route. Because now integrated steel plant, most of the steel plant has you have a DRI unit, you have the SR unit, smelting reduction unit, you have blast furnace also. So you can combine this raw material in any proportion and you can use electric arc furnace to convert them to steel. Okay. Now, let us talk about the blast furnace iron making. In the blast furnace iron making, I'll just give you some key parameters. As I said, among the all iron making processes, blast furnace still holds the dominating position, very high position still now today. More than 50% steel is now produced by BF route. And the blast furnace remain very up to date and competitive with new technology. As I said, in the SR technology, major problem is that of gas trading. And the blast furnace is a very, very energy efficient process. Its exit gas goes around 150 degrees centigrade, and the CO, whatever CO is there, you can 30% you can use in the blast furnace stove itself, and 60% for downstream application. It is well established. But in case of the SR process, that is the exit gas contain a lot of CO, and you have to utilize it unless it may not be competitive with the blast furnace technology. Okay, so that is the thing. And the hot metal production rates nowadays is around that is the 8,000 to 10,000 tons per day. These are some of the benchmark I'm talking about. And the fuel rates is around 450 to 470 kg per ton at metal, out of which 270 kg of coke and 175 to 225 kg of coal. Coal means there's the PCI, pulverized coal injection through the air. That nowadays has reached more than 200 kg, along with 270 or 275 kg of coke. Because the minimum amount of coke you have to supply into the blast furnace, because coke has a great role to play. Not only you can supplement its heat generation, you can supplement its reduction potential, but you cannot replace one of the major property of the coke, that is to withhold the overburden. So overburden, because in the lower part of the blast furnace, everything is liquid except the coke, and coke remains in the form of a dead man cokes, and that basically holds the overburden. So a minimum amount, and also that dead man coke also carbonizes the liquid iron and also gives a very porous bed for the liquid to come down to the heart. So a dead man coke is very important. And you have to give a minimum amount of coke, okay, in the blast furnace. So you cannot do away with that. So blast furnace, that is the major limitation. That is the coke you have to supply of the order of 250 at least kg of coke per ton of hot metal, along with the sinter pellets or good quality iron burden also. Achha, okay. So this is, and then the furnace availability ranging from 95 to 98%. It means the furnace almost operate, and then you don't have to interrupt the process nowadays. So you have improved the refractory line significantly such that you can operate it for a longer time, and then you can any repair work can be taken up that way. Okay. So now let us see some of the developments in the blast furnace iron making. You see how the blast furnace in 1950s, so then came the iron ore beneficiation use of overseas ore, because as I said, blast furnace, the major limitation is that you have to have a very good quality of iron ore burden. That is, the burden of the blast furnace or the raw material should be of very good quality, because otherwise you cannot maintain the permeability in the dry zone as well as in the liquid zone. Okay, so quality of the coke, quality of the iron ore, in terms of agglomerated product like sinter and pellets has to be there. And iron ore beneficiation is also required at the time. Beneficiation was also required because you can increase the grade of the iron ore. Obviously, you can increase the total iron. Then iron ore pellets use came because pellets give a very nice permeability. There's the permeability, if you consider, then pellets gives the very good permeability in the dry zone, because the lumpy ores, because they are very strong. Because when you charge the material comes from the top to the bottom, and it undergoes a lot of impact, a lot of abrasion. And if the quality of the burden material is not good, if the abrasion properties, the strength of the material is not good, they can generate a lot of fines. As a result, they can choke the blast furnace shaft. Okay, as a result, gas movement, since it is a counter-current process, is the gas movement will be affected. Okay, so use of iron ore pellets give a very nice permeability, so that came. And then oil injection. What is the, because the oil injection in 1960s or it came, middle of 60s, it came. Basically, oil injection you can supplement, that is the heat supply and the reduction of the coke. So you can reduce the coke rate by using the oil injection. If you do oil injection, you can replace some amount of the coke. And if you can replace the coke rate, that means you can reduce the coke rate. That is the per ton of hot metal, you can reduce the amount of the coke that is required. And if you can reduce it, you can increase the productivity. Because in that place of the coke, you can charge some amount of iron, so your productivity will be higher. So that was the idea. Oil injection came only for the idea of basically to increase the productivity by reducing the coke rate. Then also in the blast, there is the blast preheat. Nowadays, you can preheat the blast more than 1200 degrees centigrade, 1200 degrees centigrade. So you can give a lot of sensible heat through the blast furnace and through the air blast. And this sensible heat, you can supplement that. There is the heat generation by the coke, so you can reduce the coke rate significantly. So that is also there. And then you can, the blast furnace hot stove is basically operated by the off gas from the blast furnace. 40% of the blast furnace off gas goes to the stove to preheat the air to 1200 degrees centigrade. And that is good. So you can utilize this own heat. And at the same time, you can reduce the coke rate. So your productivity increases. So top counter pressure, then you can use the top pressure, high top pressure, especially with the bellless charging. If you do the bellless charging, the top portion, you can completely save it, okay? And then as a result, you can maintain a high pressure. If you maintain the high pressure, top pressure, so what? You can reduce the pressure drop. So if you want to increase the productivity, obviously you have to increase the blast rate. And the problem is increasing the blast rate is that it increases the pressure drop. So pressure drop increase means a lot of irregularities will come because, and then if you can use the high top pressure, basically you can reduce the pressure drops. So even at the high blast rate, even at high productivity, even at high blast rate, you can operate the blast furnace smoothly if you have a high pressure, high top pressure. So top counter pressure, bellless top charging thing. And then the burden distribution. Burden distribution has a great role to play in the blast furnace for the gas distribution. Okay, so because ore coke ratio across the radial direction is very important, because if you can maintain a less segregation between the ore and coke, obviously you can get a more uniform permeability across the cross section, and as a result, the gas distribution will be more uniform. So burden distribution has a lot of role to play. You know, where to place the coke, where to charge the coke, where to charge the ore, because you know that is the coke has a low angle of repose and the ore has a very steep angle of repose, because ore is usually very heavy, and they try to, where they fell, where at the point they try to form a ridge. Okay, angle of repose is high, but the coal basically rolled down. The coke basically rolled down. Anyway, so those things are there. So where you put the coke, where you put the ore, that is very important. Okay. So burden distribution plays a great role in distributing for the gas permeate, that is the gas distribution in the blast furnace. Improvement of the iron burden properties, that is there because you can improve the reactivity of the sinter, you can improve the reactivity of the coke, and that can be, as I will see later, if you can increase the reactivity of the coke, basically you can reduce the temperature of the isothermal zone, and that can increase the CO utilization, and that can obviously increase the productivity as well. To talk about that. So improvement of the burden quality, improvement of the coke properties. Then came the coal injection, PCI injection case lately in 1970s, basically of oil crisis, when the oil price suddenly improved because of world oil crisis. That time is the coal injection started, and nowadays people don't look back for the oil injection because coal injection now so established. So pulverized coal injection has taken its shape today. Now that is the copper steps for blast furnace cooling. It is very important because you can see the chemical life has increased more than 15 years, and one of the important reasons is the copper steps for blast furnace cooling. You have the step cooling means basically you have copper plates with the water inlet and outlet. Since copper has very high conductivity, it can extract the heat very fast, and also water cooling inside it basically increases the heat extraction. So basically you can keep the refractory cool. because you have to keep the refractory cool, because otherwise if the temperature of the refractory increases, its life will decrease. So that is the thing. If you can take out the heat from the refractory in a proper manner, then basically your Campaign life increases. And then the availability of the blast furnace, as I said, nowadays the availability is 95 to 98%. It is because of one of the reasons for that is the refractory life has increased significantly. Then waste gas recycling in the sinter plant, that is there. The waste gas, whatever is coming, 40% use up in the hot blast stove and 60% go for the downstream application. A part of it goes to the sinter plant, part of it goes to the coke oven plant. So it is nicely utilized. So your energy utilization is complete in the blast furnace. That's why it is so efficient. Inside, energy utilization is very high, and whatever the obvious come out, that will also be utilized. And very recent is the not coke charge. Not coke means that is the coke size less than 40 millimeter is called the not coke. Usually the coke size 40 to 80 millimeters, and not coke is less than 40 millimeters. 10 to 40 millimeters is called the not coke, and that is the comparable size to that of the iron ore. Okay, iron ore and is an agglomerated product. And it has been found that if you use a not coke, you can increase the permeability in the shaft significantly, because it forms a structure throughout the cross section. Okay, so basically it provides a very good permeability, and also the not coke has more reactivity, so carbon gasification reaction it increases. As a result, you can increase the indirect reduction in the blast furnace. Okay, it is very important, indirect reduction in the blast furnace. More you can promote the indirect reduction, you can utilize the CO utilization, because the blast furnace eventually the direct reduction will take place in the lower part of the furnace where temperature is high. Then carbon directly participate into the reaction by forming the in situ CO generation. Okay, so that takes place. But in the upper part is the 40. If you can thermodynamically, I can show you that if you carry out 46% of, that is the maximum possible 46% indirect reduction. If you can carry out, your thermodynamic efficiency or the CO utilization become 84%. That means that is the maximum utilization that you can expect in the blast furnace. Beyond that, you cannot go. Some amount of the CO has to leave the blast furnace thermodynamically also. Okay, so your maximum CO utilization is 84%, and to do that, you have to attain a 46% indirect reduction. And in most of the furnace that operates, the indirect reduction is much less than that, maybe 30% of like indirect reduction. So if you can improve the indirect reduction, the furnace productivity increases everything. So coke rate decreases, productivity increases, and the not coke plays a great role. The recent literature shows like that. Okay. So this is some of the developments of the iron making process, and the blast furnace, so day by day has become more and more rugged. It is very difficult to replace the blast furnace unless the SR process become very competitive by utilization of gas. So now, even there is the scope for improvement into the blast furnace, and there are two scopes is there. One is called the top gas recycling in the blast furnace. This is called the TGRBF, and the low temperature, low emission iron making in the blast furnace. Okay, and this is the TGRBF process. Basically, it is a process of the Vulkos. Vulkos represent the ultra low CO2 steel making. You may know it is a consortium of 48 European companies and organizations, and its birth was in 2004 after the Kyoto Protocol. Kyoto Protocol basically limit the CO2 emission from the blast furnace. So per ton of that is your hot metal, you should not exceed 2 tons of carbon dioxide emission. So you have to, that is usually the blast furnace more than 2 tons of carbon dioxide it emits per ton of hot metal. So you have to reduce it significantly according to the Kyoto Protocol. And then this consortium idea was there mainly to how to reduce the CO2 emission from the blast furnace. So they came up with an idea that is called the top gas recycling. What they basically do, you can find that is the exit gas they take out, and after the gas cleaning, you just scrub off the CO2, and then obviously the gas will be rich in oxygen, the carbon monoxide, and you can find here we are just charging the oxygen, not the air mist. So we are charging the oxygen, not the air blast. As a result, you don't have the nitrogen dilution of the exit gas. So there is no nitrogen in the exit gas, only CO and CO2 is there. So if you can take out, you can scrub the CO2, the most of the gas will be 100, around more than 90% will be the CO only. So this CO you can recycle back into the blast furnace. Okay, as a result, you can reduce the coke rate significantly. Okay, so you can reduce the coke rate, you can increase the productivity, and also as the coke rate is decreasing, obviously your CO2, overall CO2 emission will also decrease. Okay, so that is the thing. And so these are the features, as I said, your pure oxygen charge at room temperature, pure oxygen, that's why you don't have any nitrogen dilution. And it is easy also, because since the exit gas is CO and CO2, then it is easy to scrub the CO2, because CO2 concentration is quite high. Basically, CO2 scrubbing is done by a method is called the vacuum pressure swing. That means you first absorb the CO2 in some absorbent like zeolite or activated charcoal, and then you release the pressure so you can take out the CO2. And then you can give it for the storage somewhere. Okay. So that is the thing. And if the concentration of CO is more in the exit gas, then it is better. Okay. You can carry out this process better. And then you have a gas heater, some you heat it, and then you can push it to the blast furnace. Okay. So CO2 is separated by VPSA, and then top gas after separating CO2 is recycled back in the furnace, as I said, after preheating, because in the process you lose some heat, and if you give some cold gas, then obviously the thermal load of the blast furnace will increase. So some gas heating you do, or it will basically disturb the process inside. That's why some heating should be there, such that it enters at the same temperature of the blast furnace where you are putting it. 25% reduction in the carbon consumption. Obviously, you are recycling the CO, so that CO load of the coke is decreasing. So basically, you can reduce 25% reduction in the coke consumption. 50% reduction in the CO2 emission. That is very important. As the carbon rate is decreasing, obviously your CO2 emission decreases. And this is obviously in the pilot scale, that is in the LKAB lab of Sweden, it has been shown, but it is still not commercialized. But this technology can easily be retrofitted in an existing blast furnace. So, okay, so that can be done. So this is an available technology that can be taken out by the blast furnace. Okay, and you can, if you want to reduce the carbon dioxide emission significantly, basically, which is the trend nowadays. Okay, so next is that is the low temperature, low emission iron making technology. What is that? You can see here I have put the two diagram. This diagram, you know, it is called the FECO phase stability diagram. If you know this, it is usually in people show like that, but here I have shown it in a vertical way. It is not usually in the book. You can see in the horizontal way. It is vertical way because to accommodate this, what is that called, the HIS diagram. Okay, this is the HIS diagram is basically based on heat and material balance. You can, you know, I think the HIS diagram, basically if you do a heat and material balance, you can get a straight line. If you plot O by FE in one axis, that is the O by FE, other axis is the O by C. O by C is basically the gas composition. And then you can get a straight line based on heat and material balance, and the slope of which gives you the coke rate. Okay, how much coke is required. Okay, and this intercept gives the blast, that is the blast rate. Anyway, so that is called the HIS diagram, and this is the phase stability diagram, FECO phase stability diagram. And here what you can find is that when the isothermal zone, you can see at a particular temperature, this is this line. If you can see, this line is the Untitled iron equilibrium line, FeFeO equilibrium line. Okay, and at a particular temperature, you can see what is the equilibrium gas composition is required for that equilibrium. So you will be astonished, which basically most of you know also. Say at 1000 degrees centigrade, that is this axis is O by C. It is with hydrogen also, if it is hydrogen is there. Otherwise, for FECO phase diagram, if you consider it is O by C, if you see at 1000 degrees centigrade, O by C is around 1.3. And O by C, that is the atomic ratio of oxygen to carbon. You can write it in terms of volume fraction of CO equals CO2 mixture. If you convert it, then it will be around 70% of carbon monoxide. So more than 75, 900 degrees centigrade, it is around 75%. So 100,000 degrees centigrade may be higher than around 75%. More than 70% of carbon monoxide should be in equilibrium with the Woodstide iron FeFu equilibrium. That is this, more than 70% CO is required to maintain that equilibrium. So you can understand that utilization of CO is less. If 70% in equilibrium, that means your utilization of CO will be only 30%. So, or in other words, you can say if you want to reduce 1 mole of Woodstide FeO, then you require 100 by 30, that is the 3.3 moles of carbon monoxide, out of which 1 mole of CO will be used up to take out 1 gram atom of oxygen from the Woodstide. The rest 2.3 moles of CO will be in equilibrium. Okay, so CO-CO2 ratio will be 2.3. Okay, so that means that is your O by C is around 1.3. So you can see that higher the temperature, this Woodstide equilibrium, this CO requirement is quite high. If you decrease the temperature, so where basically most of the indirect reduction takes place in the isothermal zone, that's why I'm telling the isothermal zone. If I reduce the isothermal zone temperature to 700 degrees centigrade, then I can find that my O by C decreases significantly. That means CO utilization will be higher, or the CO requirement, equilibrium requirement of the CO will be much less, and your CO utilization will be very high. So CO utilization high means your coke rate will decrease obviously. So anyway, but if you just see this point, this is very important. Coke rate, how it will be decreased from this diagram also we can say that. Physically you can understand, if your CO utilization increase, obviously your carbon rate in the blast furnace will decrease because you are utilizing the CO in a more greater extent. So carbon rate obviously decrease. From the diagram also you can find, if you just project this line to the diagram, you can see this W is called the FeFu, that's the equilibrium point. Okay, so this point is at 1000 degrees centigrade, it is around what? That is the O by C is 1.3 and Woodstide is 1.06. There's the O by Fe ratio is 1.06 and O by C is 1.3. So this thing, Woodstide equilibrium point is there. Now, if you decrease the temperature of isothermal zone, that means if you come here, then you can see the Woodstide equilibrium point shift to the right. So what happens then? This line, this is the optimum line. This solid line is the optimum line, and if you can reduce the isothermal zone temperature, then you can find this line can be shifted to the right. That is, the slope of this line will decrease. Okay, this is the optimum line because this line cannot cross the W. Okay, so it can move in the right direction, in the left direction, but it cannot move towards the right because it will then violate the FeFu equilibrium. But if you can reduce the isothermal zone, then W point shift to this, so the optimum line will be shifted here. So the curve will much more flatter. That means your coke rate will decrease, right? So you can decrease the coke rate by reducing the isothermal zone temperature. Now this is very interesting, but how you can reduce the isothermal zone temperature? And this can be done by some method. One thing is that you can increase the reactivity of coke. If you can increase the reactivity of the coke, then the carbon gasification can take place even at a lower temperature. I know that is for ordinary coke, that is the carbon gasification temperature is around 1000 degrees centigrade. Okay, then basically the CO2 plus C forming twice CO, this reaction become irreversible. That is, the CO concentration become very high. And at that temperature, at 1000, at lower temperature, this reaction is very sluggish. Okay, but if you increase the reactivity of the coke, then possibly you can carbon gasification can take place even at lower temperature. Okay, so that's why if you can increase basically if gasification reaction take place at lower temperature, so obviously your indirect, that is what is that, your isothermal zone temperature, the indirect reduction zone temperature you can decrease. Another thing is the reactivity of the sinter. Obviously, iron reduction depends on the reactivity of the sinter. So, air reactivity of the sinter, air reactivity of the coke, and catalysis of the gasification reaction. Basically, alkaline metal can catalyze the gasification reaction. Even the fresh iron also catalyze the gasification reaction. So, these things are there. And then you can use the iron ore coal composite pellets. People also say that if you make the iron ore coal composite briquettes and you can charge. What happens in the iron ore coal composite plates is that there's an intimacy between the carbon and the iron ore increases. As a result, the mass transfer efficacy becomes very high. Okay, because that is because the gas do not have to travel a longer distance. Okay, carbon and iron ore are residing close by. So the reaction kinetics become faster. So iron ore coal composite pellets also you can try, with a lot of literatures are there that basically suggests that. And use of nut coke also, I have not written, because I said use of the nut coke also can reduce the isothermal zone temperature because the carbon reactivity increases. Then use of external reform gas in the shaft furnace, that also you can externally reform gas you can use, because then the shaft furnace and most of the reform gas basically contains hydrogen, because if it's a natural gas, you reform, hydrogen is there, and hydrogen is a better reductant than carbon monoxide. So that also helps in increasing your what is that? That is called your indirect reduction. You can do the water gas shift reaction also. That also can convert some amount of the CO to H2, and then you can charge it into the blast furnace. So that way, external reform gas with water gas shift reaction also may be good. So basically, idea is here, I have to promote the indirect reduction. If I can promote the indirect reduction, then your coke rate will also decrease. As a result, your productivity will also increase significantly. So this is called the low temperature and low emission. Obviously, if the coke rate decreases, your emission also decreases. Carbon rate decreases means emission also decreases. So any process that aims from decreasing the coke rate of the carbon rate, that is emission reduces, but not the PCI. When you are injecting the PCI by reducing the coke rate, then you can increase the productivity, but you are not decreasing the emission because you are charging the coal in the form of PCI. But you have to think that way. That is the total carbon input into the blast furnace you have to reduce the emission, CO2 emission. Now I will talk about what is the time now? Talk about some of the driving, that is the alternative routes of iron making, basically some of the DR and SR process. Now, what is the driving force? Let's see. That is the driving force for alternative routes of iron making. If you see the blast furnace cooking, this is a very nice breakup for cost of different items. Like you can see, there is the coke consumed. It is the total cost, around 40 to 50% cost of producing the hot metal in the blast furnace goes to the cost of the coke. Coke constitutes around 40 to 50% of the total cost of the hot metal production. So you can find, so coke is very costly item, okay? And that's why this is one of the reasons there is the alternative routes has come, there is the coke-free process, because we don't want, because the cost become high. Because the coking coal also, coking coal in India is very scarce, a very limited amount of the coking coal resources is there, and that too, that coking coal quality is also not good because of you have a high volatile and high ash. Okay, so we are much more dependent on the import of the coking coal from abroad, mostly from Australia, and then we blend them and then use it in the blast furnace after stamp charging, like that. Okay, but still, that's why the coke is so costly. So in India, we are looking for some process which is the coke-free process. That is one of the driving force for alternative routes of iron. Utilization of the non-coking coal. All the coking coal reserve is very less. We have plenty of non-coking coal. Why not we can utilize it? So we have to design some reactor, okay, where we can use the inferior grade of coal. That is the non-coking coal. Non-coking coal, we can use it. Utilization of the iron-bearing solid waste from the plant. Like a lot of solid waste is there. There's a tailing, sludges, blast furnace sludges, then EF dust. We have a lot of iron-bearing solid waste into the plant that we have to utilize it. Utilization of the lean grade of iron ore that people are talking in the morning session. There's a lean grade how we have to use it, and the end, finally the environment. That is the elimination of the coke oven and the sinter plant, because they pollute the atmosphere significantly. So we have to look for some process which is environmentally friendly, and where you can find some process integration. Blast furnace requires these ancillaries, coke oven, sinter plant, because of its very stringent quality of raw material recovery. So these are the driving force, and we have two major processes. One is called the direct reduction process, DR process, and it's called the smelting reduction process. And some of these processes are really very promising from Indian point of view. Now, sponge iron through the direct reduction, I'll just talk about the direct reduction is written like this. In the blast furnace also take place in the lower part of the furnace. That is, you are reducing the iron ore in presence of the solid carbon and forming Fe and CO. Basically, this solid-solid reaction does not continue for a long time. As soon as the two solid contact vanishes, then the reaction will stop. Basically, this reaction do not take place that way. Carbon do not directly take the ore oxygen from it. Basically, the reaction take place by gaseous intermediate in this way. Basically, carbon is gasified by the carbon dioxide to CO, and then this CO basically take out the ore oxygen from the iron ore and forming CO2, and this CO2 again gasify the carbon. So carbon basically take place in the reduction in the carbon gasification process. Okay. So, and this reaction is possible only at a high temperature, more than 1000 degrees centigrade. So that's why direct reduction takes place at higher temperature. In the blast furnace also it takes place in the lower part of the furnace where temperature is more than 1000 degrees centigrade, where basically this carbon gasification is very prominent. There is the in situ CO generation take place. And then if you combine this reaction, you can get in this reaction. So as if the carbon directly participate into the reduction process through the carbon gasification reaction, through this reaction. Okay. So this is a high temperature process, basically around 1000 degrees centigrade you can do it. Now initially, that is the iron ore reduction, solid state iron ore reduction in presence of the carbon or the coal was called the direct reduction. Later on, there is the solid state reduction of iron ore by reform gas. Okay, that is also called the direct reduction process. The reforming of the gas, that is the natural gas can be reformed either by the steam or carbon dioxide, and it can produce the CO and H2. This gas should produce, and then the CO is to reduce the iron ore in the solid state, and this product is also called the direct reduced iron. That is the product of direct reduction. So this is also called the direct reduction. That is, and advantage of the gas-based process is that temperature can be carried out in 700 to 800 degrees centigrade. And in case of the coal-based DR process, when you are using the solid carbon as reductant, then the process temperature should be at least 1000 degrees more than that. Otherwise, carbon gasification reaction is not very significant. Now, if you see the evolution of different direct reduction technologies with time, so initially it was the Saggars in the tunnel kiln. Okay, Saggars is basically a cylindrical refractory where basically you put the iron ore and the coal mixture, and then you put in a what is that called? In kiln, and then in a tunnel kiln means you have a long kiln is there, and there basically lot of, that is the boxes are there, boxes filled with the saggars move in that tunnel. Okay, and in the tunnel you have an opportunity for giving the burners, different burners are there. So these burners, heat from these burners basically heat up the saggars and inside material. So heat basically penetrates in the transfer direction, and then the iron ore coal mixture get reduced. Okay, so in the tunnel kiln. So it was the initial process, and it was developed by the Hoganas, and it was based on coal. All the initial process were based on coal. And that small shaft furnace also, there is the Weber process. Weber process you must have heard about. And this is also a shaft furnace based process. Usually the shaft furnace based process are run on the reform gas, and reform gas are mostly from the natural gas, but this Weber process basically was run by the coal gasification. Basically, the coal gasification was there, and then using the shaft furnace was run. And the rotary kiln process, then the rotary kiln is the most rugged process came by the Lurgi and the Crook process, which are very, this is basically the coal-based rugged DRI process. There's the rotary kiln process. And then from end of 50s, you have some gas-based process came into picture where basically the natural gas is reformed, and this natural gas reformed gas is used for producing the sponge iron. And HOL1 process was there, and that was based on the static reactors. Basically, there are 4 batch reactors, and then switching this batch reactor, they used to work. Okay, anyway, the static bed reactors, that was the HOL process, and then came the fluid bed reactor, also fire process. So they are basically gas-based, natural deformed gas, and the fluidized bed reactors are there. That is called the fluid bed reactor. Okay, so that was the fire process over there. And then end of 60s came the shaft furnace, and then the mid-rates, HOL3, all these processes came, all are based on the gas, and mostly basically natural gas, based on the natural gas, reformed natural gas. And currently you have the rotary hearth furnace. The rotary hearth furnace, I'll talk about that thing. It is a hard, basically in the rotary hearth furnace, hard basically rotate in a 360 degree, and you can put the material over the hearth in the form of iron-nickel composite pellets, and the hearth will carry the material through different temperature regime of the rotary hearth furnace, and then finally you dispose at the outlet where you can get either the DRI or the iron nuggets also. Iron nuggets also possible, that is called by the ITMP3 process. I will talk about that. So rotary hearth furnace is also evolving because since the material itself does not move in the rotary hearth furnace, so you can compromise a lot with the quality of the raw material. So you can use any kind of waste and you can briquetize them and just place on the hearth. They will not move. You just carry this material. The hearth will carry this material through different temperature regime. As a result, the reduction will take place and finally will come out. And that is the DRI you can produce from the waste material. And you can even produce the nugget, but there the quality of raw material may be required high. Okay. Then improved fluid bed, some process came like film bed process. In the film bed process, the fluid bed reactor, but here the reformed gas is rich in hydrogen. Basically, they use some water-gas shift reaction such that some CO is converted to hydrogen, and finally you get a very hydrogen-rich gas. And hydrogen-rich gas is advantageous in the fluid bed reduction process because you can reduce the furnace temperature significantly. Okay, so because at high temperature there is a chance of agglomeration of the fine particle. So if you can enrich with the hydrogen, the temperature you can reduce, those agglomeration problem is somehow decreased. And then you have the self-reforming process, that is HOL4 process, where basically the reforming, you don't have the outside reformer. You can directly charge the natural gas along with natural gas into the blast furnace, into the reactor, in the reduction reactor, where basically natural gas will be self-reformed in presence of nascent iron. But you have to put the natural gas little bit higher temperature, say 1,000 degrees centigrade, and then when they go inside it, in presence of nascent iron, there is the self-reforming is possible. So natural gas will get reformed inside the reduction reactor, and then CO and H2 will reduce the iron. So this is the development of this process, and this is just a very nice picture, a micrograph of the sponge iron, because why it is called a sponge iron? Because if you take a sponge iron, it never looks like a sponge. Okay, why it is called sponge iron? If you see the microstructure, and you can see a lot of pores into it, and it appears like a sponge. Just as if you just push it, it will just eat. Okay, so that's why it is called a sponge iron. It's a very nice micrograph with a lot of pores into it. Basically, during the solid state reduction, CO gas evolved. No? The CO comes out, making CO and CO2. As a result, you can get a lot of pores inside. So there are the different gear technologies are there. You can have based on natural gas like fire process, subcorrode, thin melt processes are there. Here basically you have iron ore fines and the natural gas, okay, reformed natural gas. And then you have shaft furnace based process like Midrex and HOL3 is there. Here you have to charge the pellets, natural gas, lumpy ore also you can use it. Then you have coal based DR process. They are lumpy ore you can use, you can pelletize also, and coal like SLRN, that is the Ludwig-based process, then the CODIR process, DAVDRC process, Alice Sharma process, Tata direct reduction process, Jindal process, OCL process, Alicia sponge. So a lot of varieties of water, there is the rotating process are also there. And then if you consider the fines based on feed bed reactor and the rotary earth furnace based processes are there, you can use the fine ore, waste oxide, and the coal. And then you have basically rotary earth furnace based process. Here basically the in-metro process, first met process, Sitcomate, Sarcofar, Premiums. These are all processes based on rotary earth furnace based process. And here basically low metallized solid is there. In rotary earth furnace, since you are using a lot of solid waste, the final product metallization may be of 70%. Okay, so then what you do, you basically melt it into the some IOFs, we can say iron making furnace or the submerged earth furnace like that, because you have to separate a lot of gangs and then you can get the synthetic hot metals and you can purify in the electric arc furnace and produce electric arc furnace. Okay, or here also they can supply all this DRI. And iron carbide is also, you can produce the iron carbide also directly from the iron ore. And iron carbide also can be fed to the electric arc furnace. Advantage of the iron carbide is that it basically dissolves because its melting temperature is quite high. But when you put into the liquid iron, basically the carbon dissolves into the iron and finally iron gets, it basically dissolves into this thing. So iron carbide is a very pure form of iron, you can say. When the carbon goes out, it is only iron, nothing is there. Okay. Typical analysis of the gas-based and coal-based DRI. If you see the total iron, coal-based is less and gas-based is high. It is not due to the process because the grade of the ore, the grade of the sponge, it depends on what is the grade of inlet raw material. Usually the gas-based process uses a better quality of raw material. That's why your total iron or the grade of the gas-based coal is little higher than that of the coal-based DRI. And the metallization obviously depends on the process efficiency. So in case of the coal-based, you have 80 to 82%, and gas-based is higher because since it is a gas-solid kinetics, it is a faster and is much efficiency is better. That's why you can get a better metallization here. And obviously the metallization, you understand, it is basically the ratio of the metallic iron to that of the total iron percentage. And then this is the thing. So how much total iron you can convert it to the metallic iron? Basically total iron in the form of oxide. How much oxygen you can take out, that basically gives you the metallization. What is the efficiency of taking out the oxygen? And that is better in the gas-based process. And it also depends on the inlet raw material also. If we have a bad raw material, obviously during the process, a lot of liquid can form because of ash, and then that can hamper the gas passage and all these things. So the process kinetics will hamper. And then carbon percentage you can find in case of the coal-based is 0.1 to 0.3 because, as I said, the solid state diffusion is very less, and that's why coal-based carbon, that is the carbon percent is less. In case of the gas-based, it is higher, even it can be more than 2 also, because you have a control on the blast in the cooling stage. Actually, in the gas-based shaft furnace, you have 2 parts. One is the reduction part and the cooling part. In the cooling part, you basically charge the natural gas. And this natural gas, at that temperature, 900 degrees centigrade, cracking takes place. And that cracking produces a lot of soot carbon. And that carbon can easily go into the, that is the austenite structure and can form the iron carbide. And then it can enrich the iron with the carbon. Okay, so you have a control. You can control those process parameters and you can have any kind of opening carbon in the gas-based DRI. But in case of the coal-based DRI, you have a limitation because you don't have such carbon increasing condition. Okay, so it is like this. And sulfur, in case of the coal-based, obviously little higher because in the coal-based process, that is the iron ore remain in close contact with the coal, and coal from the coal ash, the sulfur goes into the iron. But in case of the gas-based process, it is the reformed gas. So there is no source of sulfur. So that's why the sulfur is less. In case of the phosphorus, if you see, almost more or less similar. Okay. So coal-based DRI protection process. I'll just talk briefly about the rotary kiln process. It's a very rugged process. As you can see, basically iron ore, coal, and limestone is charred. Limestone is given basically to reduce the sulfur content. And then whatever, this is the rotary kiln, is basically a cylindrical reactor. It rotates at a certain speed and with a certain inclination such that the material can move under gravity with the rotation. And because of this rotation, it has an advantage, that is the raw material, the surface of the raw material get renewed to the surface, to the gas atmosphere. Okay. So that basically increases the kinetics as the solid surface get renewed because of rotation. So your kinetics become a little higher. Okay. And you can find here air coal mixture basically. Here basically coal is the heat generator as well as it produces the reducing gas. So air coal mixture, you burn it, it generates the heat, and then basically you produce the CO2, both the gases are produced, and here you can find some secondary oxygen injection is there. Basically because of direct reduction in the solid bed, you produce CO, the CO will come out, and that CO is combusted in the upper part of the furnace in presence of this auxiliary, there is a secondary air that you are getting, and that also supplements some amount of heat into the furnace. And then so this is the way, that is the reduction take place and the material comes here. You can do an indirect cooling, okay, indirect cooling, because you cannot expose the hot DRI, because hot DRI is very susceptible to deoxidation. So you cannot keep it in presence of oxygen atmosphere. So basically by water you cannot directly quench it, it will be oxidized and surface. So what you can indirectly quench it, okay, and after that you go to the screening, magnetic separation, and then you can get the sponge. Most importantly, basically whatever the gas is coming, that gas has to be cleaned, because whatever the gas is coming out is a dust-laden gas. Lot of particulates are there because you are burning the fine coal. So lot of dust is there. So first you have to separate the dust, and after that also, as you will see in a if we just make an energy balance, lot of CO is there in the exit gas. So chemical potential is quite high. So this gas, after cleaning, gas cleaning, that waste gas also contain significant amount of energy. Around 40% of the total energy goes away to the waste gas. So you can utilize that gas for steam generation or the power production. Then only this process will be more economic. Okay, and then you can dust. So both the things are very important. First, you have to clean the gas. Otherwise, it is very polluting. It is very polluting. So you have to clean the gas. And second thing is that the waste gas has to be utilized to make this process economic. Okay. So if you see, just give an energy balance of the rotary kiln, it is all the units are gigacalorie per ton of DRI. You can see the input energy around 5.7 to 5.8. This comes through the coal. And recirculating heat around 0.1. This is the waste gas recirculation for preheating and all these things. So majority is coming through the coal, 5.7 to 5.8. Okay. And the output energy, you can consider the sponge iron contained around 1.75 to 1.8, around 35% of the total heat. What is the sponge iron energy? Basically, you have to reduce the iron ore Fe2O3 to Fe. So that involves a lot of energy. So that goes to the sponge iron energy. Also the sensible energy, sensible heat of the sponge iron. So dissociation energy plus sensible heat, basically that counts for 35% of the total heat. And waste gas loss, if you see, around the 2 gigacalorie per ton of DRI, that is around 40% of the total heat goes away as the waste gas. So unless you utilize this process is not at all economic. And char content, that is all the coal that you give with the iron ore, okay, at the input, all are not get utilized, because after that volatile is removed, they form the char. A lot of char comes out. So you can at the exit you can get a lot of char, and the char contains a lot of energy because it is pure carbon. So 1.1 gigacalorie per ton of DRI, that is the char content that much of energy. So char also has to be utilized properly. cooling losses are not very high, 0.25 and uncooled. So this is the thing. So energy in the waste gas is significant, must be recovered to make process economical. Turbine must have adequate capacity to handle higher gas volume if volatile matter of the coal is high. So then also, if high volatile coal is used, then basically gas generation will also be much higher. The capacity of the gas will be higher, then should have a bigger. So now some of the features, you can see, if you see the inside of the rotary kiln, it looks like this. You can see only loading, solid loading is only 15%, and 85% is free phase. This is called the free load. And because of this large space, that basically facilitates the transport of dust-laden gas. Lot of gas are generated because of the coal combustion inside the rotary kiln. Is a huge, large amount of the dust-laden gas. So you have to supply so much of free load such that that gas can be transported out. Okay. So any other reactor, shaft furnace cannot deal with this situation. Okay. So this is a typical thing. That's why the productivity, you can understand, the productivity is only 15% of the total capacity. So it is 500 tons per day, one reactor. So if you want to produce, say, 2,000 tons per day, then, and so in that case, basically, if you utilize the waste gas, then it can be compensated. And another thing people can think about, that is the scope for outside carbon gasification, increase the solid loading and the productivity. If you just, instead of giving the coal directly inside the rotary kiln, if you can gasify the coal outside, and then the CO gas will burn inside the furnace, then I don't think there is the furnace so much of free load will be required, right? So because all the particulate, that is the pollution, will also reduce significantly. So coal gasification outside, if you can do, then we can increase the solid loading also. Because in that case, only the CO has to be burned to CO2, because the heat generation. It will be a much cleaner process, and also productivity can be increased. So charge rotation. This charge rotation is a very important thing. As I said, it basically removes the surface towards the gas. As a result, its kinetics is a little higher. And the rotation at optimum speed also very important, because as I'll say, there's the accretion formation. There's a very, you can see there is the accretion formation. This is a very prone to the accretion formation. Accretion means basically your buildup of solid material over the wall. And finally, you can see the space is reduced, and finally this much of space, that is the solid movement almost become difficult through the kiln. Okay, so that much of situation can be created. So no solid movement can take place after some time. This is called the accretion. And the rotation has a great role to play. Optimum rotation also has a role to play to restrict the accretion formation. Basically, when you rotate it, then the segregation takes place. That is how the coarse and the fine particles segregate. Obviously, the fine usually try to segregate towards the wall, and the coarse towards the center. Okay, so away from the wall. So as a result, the fines usually segregate near the wall, and at this wall, temperature is quite high. Basically, heat is you can see in the figure, heat goes to the wall or the refractory, and then refractory, the heat also will go to the fines, and the fines, there is the ash content. Coal contains the ash, and those ash, if some incipient fusion of the ash is possible, if some low melting eutectics are found, and that is always possible in presence of lime and presence of acids like SiO2, Fu, and all these things. So you can simply form the low melting eutectic. You can form the melting of the ash, and then agglomeration will start from the wall. So if you have an optimum rotational speed, that can restrict that the segregation, fine segregation near the wall. That is one way you can restrict the accretion formation. Another is that another method by which you can reduce the accretion formation use of reactive coal. If the coal is quite reactive, then it will gasify fast. Okay, so it will gasify. It will go to the complete gasification, and that basically helps in reducing the accretion formation. And it has a very good potential for the power generation. In fact, if you don't generate the power utilizing the waste gas, this process is not very good. Now, coal-based process other than rotary kiln process, that is a very important process. As I said, rotary heat furnace. Here the input is basically iron ore coal composite pellets are there. And you can get a sponge iron on the nugget from the outside. As I said, it looks like a donut shape you can find. And the charge enters from the inlet and it moves over the heart and passes through different temperature reading, and it undergoes preheating reduction and finally come out the sponge. And in case of the ITMK3 process, then what happens, you have another zone where the high temperature zone is there, where basically slag metal separation also take place, and then you can get the iron nuggets on the output. Okay, so there the process control and the raw material requirement is there. And also one more high temperature zone is required. Okay, and in the rotary heat furnace, as I said, charge is stagnant. That is the major advantage. Charge does not move, so physical strength of the charge is not great, is not that high. So you can reduce it significantly. So you can compromise of the raw material and you can reduce it. Okay. So what is the time? Am I? Hello. Okay.
Yes, sir.
What is the time? How much I have covered? What is the time now?
Sir, actually it is now 4:30.
Sorry. So then I have okay. Okay, this is the first minute process where basically your product is hot briquetted iron. There is the fines are agglomerated here. Okay, so you can have basically in the first minute process the product is sponge iron, or you can produce is hot briquetted iron and then you can transfer some. Because what is the advantage of hot briquetted iron is that you increase the surface area, so deoxidation tendency become less. Okay, or you can hot charge also directly into the electric arc furnace. And also this is the basically the ITMK3 process. As I said, in the high temperature zone, you can have a very solid, that is the iron slag metal separation, and you can get the iron nuggets. And these iron nuggets, you can hot charge in the plant itself if you have electric arc furnace, or you can nugget, you can lab from, you can melt in. So these features I am just excluding. And that is the most important thing in the rotary heat furnace is that nowadays you can use that is the iron bearing solid waste from the plant. Okay. Now gas-based DR process, as I said, there is the fire process is modified by the Finmet process, but major problem with this Finmet process, the advantage is that you can make the reformed gas enrich in hydrogen by CO gas shift reaction, and then you can utilize and you can produce at a comparatively lower temperature. And that is the advantage. But major problem is that in most of the case, fluid bed reactor, you have to operate at a very high pressure. In this case, it is around 12 atmospheric pressure, because otherwise it is difficult to maintain a fluid bed reactor. It is not simply like that. If you don't have a high pressure, then whatever the gas you are giving, that will form a slug and go away. It will not be intimate contact between the gas and solid. It's not easy. That is, you are just fluidization. It's not very easy for the way you are fluidizing the fines. So you require a very high pressure, and that is the bottleneck for the fluidized bed reactor. In most of the cases, fluidized bed reactor, in spite of very excellent modification in the process, this process did not survive. Just like Finmet also did not survive too much. That is that it has two plants, one in the Venezuela, and you know it is a very good source of natural resources up there, and another is the Australia. So Australia also headland, that plant, this is the plant view of the headland plant, and that also reduced, that basically stopped production because of an accident. And in Venezuela also, this production is going down. So, and this is another fluid bed reactor. There is a circular process here. 100% hydrogen is given, and hydrogen, as I said, you can produce the hot metal. This is a much lower temperature. So that is the advantage. But this process is also not in use. Okay. So now the SAP furnace-based process. This is the fixed bed process. Is HOL3 process. It was based on the 4 reactors, you know, and later on it was converted to a single SAP reactor. Okay, like this HOL3 process. And in HOL3 process, basically you are steam reforming the natural gas and then you are replacing it. That is this thing. And in case of the mid-dex process, I've just not talked about. In case of mid-dex process, which is the most popular process, they are basically use there is the CO2, that is from the exit gas, you can clean the gas, and then the CO2 you can reform. You can reform the natural gas by the CO2, and then you can use it into the furnace. So both are the similar process. That is that way. Only in case of the mid-dex, your CO2 is used for reforming the natural gas. In case of the HOL3, is basically the steam is used as the reforming gas. Okay, and the HOL process has some other features. And this is the self-reforming process. It's nothing basically, as I said, there's a natural gas directly goes into the reduction unit, and before that you have just at 1000 degrees centigrade, and you can see exit gas CO2 after removing the CO2, CO gas also join the natural gas. So in this case, this is the self-reforming process. Smelting reduction process, I already have discussed about the features of the smelting reduction process. And the major features, as I said, that is this is the two-stage process. Okay, and this reactor is the most popular reactor. You partially reduce iron ore and then you use it into the metal gasifier, and then in that way you can reduce the coal rate to some extent. Basically, this process, the coal rate is very high. In case of the single reactor, in case of the Rommel process, we will find the coal rate is very high. If you do a 2-reactor process, the coal reactor decreases by 50%. Okay, but still it is high. Then it is around 2 times that of the blast furnace. Blast furnace is run with the carbon rate of 500. Here it runs with a 900 like that. And in case of the single-stage reactor, it may run with a say 2,000 2 tons per ton of hot metal like that. Very high coke rate is there. Okay. And this the single stage is a 2-stage. You may have a 3-stage reactor also. You can apply some gasifier externally. Then obviously it will increase the process efficiency. But still, this is the codex process. That is the 2-stage process. You can see this is the reduction unit. You partially reduce the iron ore and then you charge the metal gasifier. Okay, and you can find there's a coal and oxygen is charging from it, and then all circulations are there. Basically, you are recycling the gases, and finally this is the export gas. This export gas you can use it to produce the DRI, or you have to use it for the power generation. This is the finished process. You can see here the fluid bed reactor is used, and then there is the iron ore fines. Then it is called the hot. That is the consolidated iron. Basically, you briquette it, and then you charge it into the melted gasifier. Similarly, the non-coking coal also after drying, you briquette it, and then you charge into the melted gasifier, and then you can do it. And also you operate a oxygen plant. You can run a power plant, and that can support the oxygen plant that is required because you are charging the oxygen fluid as the reactor, and also into the gasifier. So this is a single-stage process that is called the Rommel process. Here, basically, iron ore fines or coal fines directly charge into the single unit. You melt everything and you then refine it. Okay, and in this case, you can find some active path is there where basically slag metal refining also take place. As a result, you can remove the impurities also to some extent. So the major advantage, the features of the Rommel process. This is a Russian technology, and this is also not commercialized, but pilot plant scale has been produced successfully, and the steel plant waste like mill scale, blast furnace, LD dust, dry sludge from the gas cleaning plants, iron bearing, one plus melter slag, oil is still turning. So every waste material you can use it, and its scale around is 1 million ton production also has been done, and excellent hot metal quality because of the active bath. Your carbon silicon you can find, manganese is also less, sulfur is less, temperature 50 degrees centigrade. And Rommel hot metal contains around 50% of the input phosphorus and 30% is partitioned into the slag. But major thing is the coal rate. You see the coal rate is very high, 1,500 to 2,000 kg per ton of hot metal, around 2 ton per ton of hot metal. So it is a very high coal rate. Obviously, the export gas will be very rich in CO unless you utilize, it has no prospect. That's why, because the first plant was at Novelis scale at the iron steel works in the Russia, and 0.2 million ton capacity, not a much success today, we don't find. And then flow sheet of his melt process. It is a unique process. You can find here, it is the smelting reduction unit, single stage melting reduction units where pure oxygen is not used. You are using a preheated air blast with oxygen enrichment. Obviously, with some oxygen enrichment, you are using the preheated air blast. And it is also charged just like in the LD. It is lens from the top. Okay, and you can form a emulsion defining in this stage you can find. And also another thing is that iron ore feed, that the fines are injected, okay, at a high speed into the liquid metal such that the capture capacity become high. Similarly, coal also in a fine state you can inject into the liquid still. Otherwise, you cannot dump the fines over the liquid. It will never melt. It will just float over it. Okay, so you have to inject it at a very high speed, and in that case, your melting efficiency, capture efficiency of the liquid also become very fast. Very fast dissolution will take place. And another thing is that you are giving a lot of sensible heat, so your cold rate will decrease. Eventually, the cold rate is very low here. So because you are giving a lot of sensible heat through the preheating of air blast, and because of this emulsion formation refining, your hot metal quality is also very high, very low impurity. And that is the thing. So you can find. So it looks like it is very. I like this process very much. It has a very promising, I think, but possibly its investment cost may be a little higher because a lot of injection systems, all these things are there. Otherwise, technologically, I find it very lucrative. And then you can see there is a 5 to 6% diffuse there in the slide, and you can reduce the phosphorus to a very, very low level. So you can find 4.3 to 4% carbon is there. Phosphorus silicon levels are extremely low. So it is almost still only carbon has to take out. So that's all. So you can produce the steel out of it. And also its coal rate is very less. So export gas credit is not that high. And finally, you have the Hisarna process that is basically developed by the Tata Steel Europe and the Rio Tinto. And in this process, what you can find, you have that is the here is the smelter vessel is there. Smelting reduction vessel is there, and this is called the cyclone converter furnace at the top. And the uniqueness of this thing you can find, that is whatever the gas is coming out, most of the gas is post-combusted. There is the CO is combusted to the CO2, and all the heat is generated, and this heat is used up into the cyclone here, and the iron ore, very fine iron ore feeds are given there, and in the cyclone it basically completely melts, okay, and also partially reduced, and it trickles down through the wall to the melting vessel unit, okay. And the uniqueness is that since you are combusting most of the CO, that is all the CO your post combustion is taking place, so your coal rate also become less. So that is the thing. And also another feature is that the exit gas almost pure CO2. So if you want to capture the CO2, you have plenty of scope. You can capture the CO2, okay, and you can reduce the CO2 emissions significantly. So that's why this Hisarna, basically capex, there is the capital investment and the operating cost are also lower than the blast furnace. Wider range of raw material. You can use any kind of alkali raw material and all these things. Iron bearing solid waste from the plants. 20% lower energy use because your carbon rate decreases significantly, as I said. If you are replacing the post combustion this completely in that type of reactor. And 20% lower CO2 emission. If you can capture the CO2 from the top, then 80% lower CO2 emission than that of the blast furnace. And the pilot plant demonstration with 6-month continuous production has been given. And it has also very good potential of coming out as a reactor in near future. So prospect of DR and SR process, that was, I can say, the rotary kiln future with the gas cleaning, power generation, and external coal gasification is a good potential. Rotary kiln also has a potential. If you can just pay attention on the gas cleaning, power generation, as well as if you can do the external coal gasification. And the rotary earth furnace, this process to utilize the iron bearing solid waste from the plant. And with this, using the coal-based synthetic gas, and already JSPL has put up a unit in the Angul, where basically the Luki-based coal gasifier is used to supply the gas, and mid-dressing unit is used to reduce the iron ore. So it is a very, very welcome, and the JSPL has adopted. It's very good. Sorry. And the SR process, the hot metal production is, and the SR process most advantage is that you are producing a hot metal similar to that of the blast furnace, even better than that of blast furnace by using a non-cooking coal. That is the most important point. And Codex is the most popular. India has a lot of units. JSW has 2 units. CSR has 2 units. Now it is ArcelorMittal. So they have more than 2 units. That is units of 2,000 ton capacity. And his belt and Romel process potential single stage SR process utilizing the plant waste. That's why this has also very good potential. Only in case of the Romel, some attention has to be given to reduce the coal rate. And his belt already the coal rate is less. And the Hishanna is a very energy efficient low carbon process with CO2 and the stop gas and discussion. So with all these things, I am hopeful that is this DRM SR technology is growing and it will grow further. And this technology definitely will change the shape of current steel making process. One day you can find there's a Hishanna type of producing only the steel. Okay. Thank you very much.